Start off by just doing a really quick review of absolute value and what that's all about. So we know that we write absolute value like this, right? We use absolute value bars to enclose something, and that's what we call an absolute value function. And we know what absolute value does probably, right? It means the distance of if I take the absolute value of a number, it's telling me how far that number is from 0 on a number line, right? So for example, it's always positive, right? Distance is always positive. What's the absolute value of 7? 7. What's the absolute value of negative 3? 3. Always makes it positive, right? Okay, and so we can see that the absolute value, here we can see right here that it's 3. One way to visualize that, like I said, is that it's just the distance from the origin. So it's 3 away, and so therefore the absolute value of negative 3 is 3. Okay, so you knew all that stuff. Just quick, simple review. Let's move forward a little bit and let's look at some algebra involving absolute values. So we're going to start very simple. We're going to solve this absolute value equation. It's an absolute value equation because it has an absolute value function in it, and it's an equation, right? So let's think about this now. What are the possible values of x that are going to satisfy this equation? And remember, that's what we mean by solution. And when we're looking for the solution or solutions to an equation, we're finding all the values of the variable that satisfy the equation, make it true. So I want to just take a second, think about that. Maybe even just with your neighbor, just check your answers. See if you can come up with 2 of them. Okay, and just run that by your neighbor real quick. Okay, so what do we got? What's the verdict? Yes, ma'am.
Wait, what did you like? I don't understand.
So what could x equal? What's one value of x that would make that true? 5. X could be 5. What's another one? Negative 5. Perfect. Could be either or, right? So far, no big deal, right? Okay, I need you back up here. Okay, so piece of cake, right? So far, so good. We know those are the values that would make that work. Let's try something a little more difficult. How about something that looks more like that? Okay, now it's not just a plain old absolute value of x. This time, it's an absolute value of some expression involving x. So we got some absolute value function equals c. Now, of course, c has to be greater than 0, doesn't it? Right? Because if we're taking the absolute value of something, it always is going to make the answer positive, right? So that's given. The question is, how could we find all the values of x that would make an equation like that work? Now, we can't really do much with this at this point because we don't know what a, b, and c are, but they're just numbers. They just represent numbers. In general, though, what could we do to solve for the values of x that would make that absolute value equation true? Think about this in terms of, now in math, there's an important word in math, an argument. The argument of the absolute value function just means everything that's being put into the absolute value function, everything that's enclosed by the absolute value function. So I'm going to put it in a red bubble. Maybe. Oh, you know what? That's way off. Okay, hang on one sec. I got to calibrate this a little bit. This is bad. Let's try this again. So I'll put it in a red bubble. So everything in the red bubble is the argument. Now I want you to come up with, is there a scheme here, a strategy I could come up with to find all the values of x that are going to make that red bubble equal c? Suggestions? Say it again.
Absolute value of b plus c.
Not quite. And I'm glad you said that, though. Absolute value of b plus c. As it turns out, algebra using absolute value bars is very complicated. It's tricky. We don't want to do it. So our strategy is going to end up being, we want to make a trade. We want to be able to trade this absolute value equation for some other stuff that doesn't use an absolute value in it anymore. Okay? So, any ideas? What if ax plus b were to equal c? Would that work? Wouldn't that be okay? Because if ax plus b equaled c, then the absolute value of c would also be c, right? So that's one possibility. The argument of the absolute value function could equal the number outside. What else? What else could it maybe equal? ax plus b could also equal what? What do you think? Could it equal the opposite of c? If it did, if it equaled negative c, wouldn't the absolute value just turn it positive anyway? Ah, so there's our strategy. That's it. That's the trick. That's the only new thing we're learning about solving absolute value equations, is that we want to make this trade. We want to always trade the one absolute value equation for two regular equations. Okay? Whatever is inside the absolute value bars, either it's going to equal the number outside or it equals its negative opposite, and we just solve those two normal equations to get our two solutions. That's it. Okay, let's look at an example. I think when you see it with numbers, maybe it's easier to see. And we got to make sure the absolute value is by itself before we do anything. So what about this one? I've got the absolute value of 6x minus 3 is 15. So there's our argument of the absolute value function, 6x minus 3. So what's the trade that I make here then? Yeah, okay, say it again. No, I can't do that. I can't change the absolute value bars. It's a good suggestion. The suggestion is, does the absolute value turn that negative 3 into a positive 3? And it doesn't, because remember what I'm trying to do here. It's a subtle distinction, but there is a difference. We're trying to find the values of x that are going to work with positive 6 and negative 3 to give us answers that equal 15, right? But what's the trade I'm going to make? Okay, whatever's inside the absolute value bars, the 6x minus 3, could either equal positive 15 or it could equal negative 15, because then the absolute value would turn it positive, right? And so this is, all we have to do is just remember this is the recipe. Whoops. This is the recipe. Can do that. Whatever's inside is either set equal to positive 15 or it's set equal to negative 15. We just treat both of those cases, just solve them both. Get our two answers. In both cases, what are the steps I go through to isolate x? First I add 3, good, then I divide by 6, and those are the two answers I get. Okay, now we can check them. We can plug them in. If I put 3 in for x, I'm going to get 18 minus 3 is 15. Absolute value makes it 15. If I put in negative 2, I get 6 times negative 2 is negative 12, minus 3 is negative 15. Absolute value makes it positive 15. They both work, don't they? Right? Okay. What about this one? Now don't jump into it yet. Take your time. What's the first thing I got to do there? Yeah, got to get the absolute value by itself. So the first thing I have to do is add 3, right? Once I get the absolute value by itself, now I can make my trade. I always want to make that trade. I want to get rid of the absolute value stuff because that's weird. They're weird. They're just strange. You know, they're hard to work with. So what's our trade going to be? 2x plus 7 equals 11. Or 2x plus 7 equals negative 11. Right? And that's the new part. Now it's old. Now we just solve it like we normally would. Right? Just subtract 7 from both sides, divide by 2, got my answers. Okay? No big deal. All right, so there's how we deal with solving absolute value equations. Now, the last two things we got to look at are the two cases for solving absolute value inequalities. We got two things we have to consider. There's two different kinds, two cases. We could either have the absolute value of some expression is less than a number, or the absolute value function is greater than a number. And we got to deal with those two cases. They're going to be different. Now let's take to figure this out. One way we could do this. Let's try a specific function. Let's try one like this. How about if we do the absolute value of 2x plus 1 is less than or equal to, we'll do less than or equal to, same idea. Less than or equal to 3. Okay? And let's see if we can find, what we want to find is what does that solution set look like? Let's graph all the places the ant could walk, the x values he could walk on to make that true. Okay, graph the solution, all the values of x that would make this inequality true. try some points. What about x equals 0? Is that going to work? Is that going to make that a true statement? Okay, take a second and think about it. If I plug 0 in for x, is it going to tell me something true? It will, won't it? If I plug 0 for x, 2 times 0 is 0 plus 1 is 1. Absolute value makes it 1. Is 1 less than or equal to 3? It is. So 0 gets graphed. What about 1? 1 times 2 is 2. Plus 1 is 3. Absolute value leaves it 3. Is 3 less than or equal to 3? It is. But that's where I have to stop, isn't it? I can walk up to that point, but if I pick a number bigger than 1, it's not going to work, is it? Right? Like 1.1 would give me 2.2 plus 1 is 3.2. That's too big, right? So I can go up to and including 1. That's as far as I can go to the right. Well, let's see if we can walk to the left a little bit. What about negative 1? And that would work, wouldn't it? Negative 1 times 2 is negative 2, plus 1 is negative 1. Absolute value makes it positive 1, right? And 1 is less than or equal to 3. That works, right? So negative 1 works. What about negative 2? That works too. Negative 2 times negative 2 is negative 4, plus 1 is negative 3. Absolute value makes it positive. And 3 is less than or equal to 3. But that's as far as I can go, isn't it? If I go further to the left, I'm going to end up getting, the absolute value is going to kick out numbers too big, right? Make sense? Okay, so I want you to tell me now, that's the solution set that we graphed. Does that look like, what's that look like that we dealt with yesterday? Maybe we recognize that. We've got a set of values of x that's bounded on both sides. Is that an OR inequality? It's an AND, isn't it? ORs were the, or remember that's ORs on the boat. Those go out to the side. The AND compound inequality, the graph looked like a single interval with boundaries on both ends, didn't it? Okay, so that tells us this is going to yield, when we make our trade, we're going to get a compound inequality that's an AND inequality. Okay? And we're right, that's how it works. Okay, this becomes an AND problem, and look at our recipe. Now this is simple to follow if you really pay attention. This, you get this one down and you'll have it. Look at the recipe here. Whatever is inside the absolute value bars, the argument, just goes in the middle of that AND inequality, right? Now what are the boundaries going to be? Well, those come from the number, right? The argument is going to be pinched between negative C on the left. So whatever that number is, its negative opposite is going to be the left boundary, and its positive value is going to be the top boundary, right? So that's the trade we make. So this kind of an absolute value inequality, we trade for two inequalities in the form of a compound AND inequality. And then what do you suppose happens down here? What do you think? That's an AND. What's this one probably going to be? It's going to be an OR. Yeah. We trade this one for an OR problem, and look how this one goes. Now, how are we going to make the positive right OR, hang on, yeah, positive right OR for you guys, and the negative left OR of the boat, right? So I'm rolling towards you along the number line. So let's see, we want the negative one has to be to the left of the left boundary, right? How are we going to say that? Well, whatever's inside the absolute value bars, then is going to have to be, whoops, I'm going to do this one first, is going to have to be less than the negative number. It's way out there to the left, isn't it? Left, less than, right? The positive OR on the right is going to be the one that's greater than or to the right of the positive endpoint. Make sense? Okay, so once again, the recipe is whatever's in the absolute value bars is either less than the negative number or greater than the positive number, right? Let's look at a couple examples. See this work. Oops. Okay, forget what you just saw there. Ignore that. Is that AND or OR? Okay, it's AND, right? Now, more importantly, why is it AND? What makes that an AND compound inequality and not an or compound inequality. Exactly, it's that sign right there. It's the less than, or in this case, the less than or equal to, right? So this is what makes it, this is what you gotta remember. That's the part that makes it and. Okay, it's that direction of that inequality sign. And then once you remember that it's and, it's a piece of cake. Then we know that whatever is inside the absolute value bars is gonna go in the middle, right? So that is going there, right? And then it's gotta be pinched between, if the number outside is a 21, if the absolute value of 4x minus 9 is less than or equal to 21, then 4x minus 9 is greater than or equal to negative 21 and less than or equal to positive 21, just like a number line. The negative 21's out there, the positive 21's out there, right? And then I just solve it like I did yesterday. From there on, it's nothing new. That's the new stuff, is making that trade. Now we move back into the old stuff that we've been practicing. So what do we do to solve for x? What do we do first? If I want to isolate that x? Add 9 all the way through. Right, so negative 21 plus 9 is negative 12. 21 plus 9 is 30. Right, now I just have 4x. Last step? Divide by 4. And that's what I get. Negative 12 divided by 4 is negative 3. 30 divided by 4 reduces to 15 halves. That's my answer. And notice if I graph this thing, I'm going to get a solid dot at negative 3, a solid dot at 7.5, 15 halves, and everything in between gets shaded because it's an and statement between, right? Questions? Okay. What about this guy? What do I have to do on this one? First thing I have to do, just got to subtract 3 because I got to get the absolute value part by itself. Okay, now what? Got to make a trade, right? I've got absolute values in this inequality, so I got to trade it for 2 regular ones. But is it going to be an and or an or?
Or.
How come?
Greater.
Yeah, the greater than part, right? It's the direction of that inequality sign that tells me. Once again, here's why it's or. Those two go together. And then how do I set that up? Whatever's inside the absolute value bars, 3x minus 2 is what? What's one possibility? Can you say it again? Greater than negative 8? No, it's got to be, now, if I'm taking the negative 8, that's going to be the one out here. That's going to be that or. I got to say, if this is the end point at negative 8, I want the or to stick out that way into the water, right? So it's got to be less than or equal to negative 8, doesn't it? Right? So the 3x minus 2 is either less than, now they got this backwards, less than or equal to negative 8, or to make the right or, I got to be greater than positive 8, or greater than or equal to positive 8 in this case. Right? Make sense? Okay, now I just solve them both. Add 2, divide by 3. And I got the 2 cases. If I graph it, it's the ors on a boat, right? I got my left boundary at negative 2, less than or equal to, shoots me off to the left. My right boundary at 3 1/3, right? 10/3, greater than or equal to, shoots me off to the right. Got it. Okay, last one I want to do. They didn't have a hard enough one, so I wanted to make one of my own here for you. The hardest one I can think of. What am I going to do with that?
Well, you're going to solve it.
I'm going to solve it. Okay, now it's an absolute value inequality, so I got to make a trade. Am I trading for an and or an or? It'd be an and, isn't it? Okay. Now, can I get rid of that negative sign in front of the 2? No, I can't. I can't do that because I'm trying to find the x that goes with negative 2, right? So this becomes then, if it's an and inequality, where does that go?
No.
In the middle. Negative 2x plus 1. And then it's going to be greater than something and less than something. What's the left number going to be? Other side? Good. And then what are the 2 steps I'm going to do in order to isolate x? First I Subtract 1, let's do that. So those cancel, and I got my 2x, negative 5 minus 1. 5 minus 1. Have I changed the inequality sign directions yet? Have not. Okay, oh, and that's supposed to be negative, isn't it? Yeah. Last step. Okay, we're going to divide everything by a negative 2. Okay, those cancel, right? So far, so good. Oh, let me get you, hang on, losing some people. We're almost done. We're just about there. You can work on this stuff. So the negative 2's cancel, and I got an x. Negative 6 over negative 2. Positive 3. Negative 4 over negative 2. Okay, but what do I have to do? Gotta flip the signs. I divided by a negative, so I gotta flip the signs. So the only problem I've got is that's not written the right way, is it? What must I do to that? What do you think? Good, I gotta do the glass trick. Gotta turn the glass this way, right? So the 3 ends up there, the negative 2 ends up over there, the x is the pivot point, that stays in the middle, and these other guys change too, right? This one goes there and flips, that one goes there and flips. Now why is it important that those switch? You might be asking. Well, what if, here's where we could have an issue when we're dealing with these inequalities. What if this one had been had an equal sign attached to it? Then that would have gone there, wouldn't it? That's the only reason. And it's not going to do that for absolute value ones. But for the other compound inequality problems in the previous assignment, you might have to be careful about something like that. Okay, make sense?
Yeah.
All right, let's go. Let me see. I'm not sure. I got to see what's free here.